Section 4.3, we were talking about interaction forces. So what happens when you have two forces counteracting one another or one stronger than the other? But essentially we're talking about two forces at play here. So, and usually it has to do with gravity. So what's important is forces always come in pairs. And we talked about this in section 4.1 and 4.2. They always come in pairs. So if I have gravity acting downward and I'm standing on a floor and I'm not sinking, that means the floor is pushing back up on me at an equal force. If it wasn't, I would be sinking into the floor. So interaction force is two forces that are in opposite directions and have equal magnitude. So if we look at the balloon in the picture, the air is rushing out at the same force that the balloon is going forward. These forces really are equal to one another and cancel one another out. Now if the balloon moves, the outward force would be slightly greater than whatnot. So that is kind of Newton's force. You have the force on A is equal to force on B. For every action, there's an equal and opposite reaction. And as we talked about, it's going to be gravity a lot, being one of the forces, and then the second force being tension or a spring or the normal force, two forces in which we are going to talk about here. So we have forces on ropes and strings. Anytime you're holding an object on a string or above on some type of device, whether it's a rope or a string or whatever you're hanging it from, you're going to have force of tension. Now, for all intents and purposes, we assume that the mass of the string is so small that we can neglect it, just like we are neglecting air resistance when we talked about gravity in chapter 2 and 3. So when we talk about the force of tension, it's F of capital T. So we have two main forces at play. You're going to have the force of tension on the string counteracted by the force of gravity. What is that going to look like? Well, if we go ahead and do a problem. All right. Example. A 50-kilogram bucket is being lifted by a rope. The second you hear rope, you know the force of tension is in play. The rope will not break if the tension is 525 newtons or less. The bucket started at rest, and after being lifted 3 meters, it is moving at 3 meters per second. If the acceleration is constant, is the rope in danger of breaking? Now, what's key here is we really have to figure out two problems, just like we did for the elevator problem. We first should figure out if the rope will break when the mass is at rest. That is very simple to do. So we'll figure out whether or not the rope will break when the mass is at rest. If it does, if the rope does break, we're done with the problem. If it doesn't, we're going to have to go and figure out what is the force of tension on the rope when the pulley is moving. So if we draw a little picture here, we're going to have a pulley. We're going to have a pulley. And essentially, we're going to have a rope, and I'll make my rope yellow, just like this. And on the end of the rope, we have a bucket. Right. Now, there are two forces at play here. We have the force of gravity pulling downward, and we have the force of tension going up. So if we are to make an equation to solve for this, since we only have two forces at play, our net force is equal to the force of tension plus the force of gravity. Now, just like we talked about yesterday with the elevator problem, if the bucket started at rest, right? The bucket started at rest, F of net is mass times acceleration, which is equal to the force of tension plus gravity, and we know gravity is m of g. But if the bucket starts at rest, there is zero acceleration. So you're going to plug in 0. You're going to have m times 0 is equal to the force of tension plus the mass of the bucket. And we could go back and plug in the mass of the bucket here. So it would be 50 times 0 is equal to the force of tension plus the mass times gravity. And remember, gravity, we have two forces, so gravity is acting downward, so it's negative 9.8. Well, 50 times 0 is 0. Force of tension minus 50 times 9.8, which ends up being 490. So we know that at rest, the force of tension on the string is 490 newtons. So the rope will not break at rest, but we have to then go ahead and solve. Now we know it won't break at rest, but what about when it initially is at motion and we have a constant acceleration? Well, here's where we start throwing things together. We can take the equations that we used in Chapter 2 and Chapter 3, and we might have to apply them to equations that we now have in Chapter 4. And that's kind of how everything's going to start to work for the rest of the year. So if we highlight everything we have a 50 kilogram bucket. All right. The bucket started at rest. That's our initial velocity. After being lifted 3 meters, that's our distance, it's moving at 3 meters per second, our final velocity. All right. Acceleration is constant, and that is what we're going to have to solve for, is acceleration. So if we go down here, all right, let's write down everything we just had. We knew our VI was 0. We know our VF was 3. We know our D was 3. And we are trying to solve for acceleration. Now, why are we trying to solve for acceleration? Well, we're going to use the same exact equation again. F of net is equal to the force of tension plus the force of gravity. Well, we go ahead and we plug things in. F of net is mass times acceleration. That's equal to force of thrust plus force of gravity, which is equal to m times g. We know, though, that now we have acceleration. Right? We have this acceleration because it says the bucket is moving. Well, when it moves from a rest to any velocity, it's going to have acceleration. So we need to go ahead and solve for that acceleration. Well, on the left-hand side, we've outlined initial velocity, final velocity, distance, and acceleration. Well, you know an equation that you can help solve for that. Vf squared is equal to Vi squared plus 2AD. Go ahead and plug everything in. 3 squared is equal to 0 squared plus 2 times 3, actually, A times A. Gosh darn it, sorry about that, guys. 2 times A times 3, which is the distance. We go ahead, we have 9 is equal to 6D, or 6A. We divide by 6, and we just solved that our acceleration is 1.5 meters per second squared. Well, what are we going to do? We're going to take this value now and plug it up in here. So now let's go ahead and do this. We're going to do the same exact equation that we had before, except we're going to add in our acceleration. So our mass is 50 times 1.5 is equal to the force of thrust plus mass, 50, times, again, gravity's acting in an opposite direction, so it's going to be negative 9.8. 50 times 1.5 is 75. That's equal to force of thrust minus 490. Or force of tension, sorry. You go ahead and add everything into the force of tension. You go ahead and solve. You get the force of tension is 565 newtons. And that means the rope will break. So oftentimes what leads to confusion here is I get asked, what is the equation for net force? Well, net, you're solving for force, so force is mass times acceleration, but the net force is the sum of all your forces in your problem. So when we went up and looked at this, we really had two forces at play. We had our force of tension plus our force of gravity. Add those two forces together, and that was our equation for net force. So net force is equal to mass times acceleration. And when you set up the equation, it's the sum of all forces in play. So we will continue to work on that in class. So we just talked about force of tension. We've talked about force of spring a little bit. The last thing that we need to talk about is the normal force. The normal force is any force exerted by a surface on another object. So if we look at the example down below here, we have a box. All right. We have a box that is resting on green ground. Or if I have a box right here just resting on the ground. There are two forces acting on that box. There's the force of gravity pushing downward, but then the surface is pushing upward, and that surface pushing upward is the normal force. The normal force, if an object is at rest and is not moving, is not sinking, not doing anything, the normal force is equal to the force of gravity. And that will come into play when we start talking about forces. So as we talked about in section 4.1 yesterday, there are tons of forces at play. We have tension, we have springs, we have gravity, we have the normal force, we have thrust. There are many types of forces. And we got to kind of try and figure out and decipher which one we're using, why we're using it, and then put together the net equation for it. So essentially, we're going to have a few problems based on this rope problem in class tomorrow. So if we have questions, we can go over that. Other than that, I hope you guys have a good night.